Ladies and gentlemen, today, I am here to talk to you about a marvel of engineering that has played a pivotal role in the advancement of aviation, aerospace, and many other fields of science and engineering, and the wind tunnel. Wind tunnels are extraordinary devices designed to simulate the effects of airflow over various objects, from aircraft and automobiles to buildings and bridges. Behind the seemingly simple concept of a wind tunnel lies a complex engineering endeavor that has reshaped the way we design and understand the world around us. The fundamental principle behind wind tunnels is the recreation of air movement over a physical model or prototype. This process involves two key components: the air handling system and the test section. The engineering ingenuity begins with the creation of a controlled and uniform airflow. To achieve this, engineers design sophisticated systems of fans, compressors, and ductwork that can generate high-speed, stable, and turbulence-free airflows. The concept of a wind tunnel revolves around replicating the behavior of air as it flows over an object of interest, whether it's an aircraft wing, an automobile, or a skyscraper. This endeavor begins with engineering precision in the creation of a controlled and uniform airflow. Achieving this controlled airflow is no small task. Engineers must ensure that the air moving through the wind tunnel behaves as closely as possible to the real-world atmospheric conditions that the object would encounter. To initiate this process, the heart of the wind tunnel is the air handling system. This system is meticulously designed to generate the desired airflow parameters. It involves an intricate network of fans, compressors, and ductwork, all working together harmoniously to produce high-speed, stable, and turbulence-free airflows. The selection of the appropriate fans and compressors is crucial to achieving the necessary airspeeds, which can range from subsonic to supersonic or even hypersonic, depending on the purpose of the wind tunnel. Engineers must consider a multitude of factors in this design process. They need to account for the specific requirements of the experiments to be conducted in the wind tunnel. For instance, the wind tunnel used to test an aircraft's aerodynamics at high speeds will require a different air handling system than one used to study the airflow patterns around a car or a bridge. The dimensions of the tunnel, the power of the fans, and the configuration of the ductwork all play vital roles in creating the ideal testing environment. Moreover, maintaining stability and uniformity in the airflow is a challenging task. Even small disturbances or irregularities in the air can skew test results. Therefore, engineers must meticulously balance various factors, such as the size and shape of the ducts and the configuration of the fans, to ensure that the air flows smoothly without turbulence. Computational fluid dynamics, CFD, simulations are often employed to fine-tune the design and optimize these airflow characteristics. The air handling system must also maintain precise control over environmental factors like air density, temperature, and humidity. These factors can significantly affect the aerodynamic behavior of the object being tested. Consequently, the design incorporates heating and cooling systems, as well as humidity control mechanisms, to mimic specific environmental conditions. In essence, the engineering feat behind the air handling system of a wind tunnel is all about recreating a controlled, repeatable, and realistic airflow environment. Achieving this requires not only technical expertise but also a deep understanding of fluid dynamics, thermodynamics, and precision engineering. The result is a remarkable tool that enables scientists and engineers to explore the complex world of aerodynamics, ultimately leading to innovations in transportation, construction, and many other fields. The air handling system must precisely control air density, temperature, and humidity, as these factors can significantly impact the results. Engineers must take into account the fluid dynamics equations to ensure the air behaves as expected. Achieving such control is no small feat and demands meticulous attention to detail and precision engineering. Moreover, the size and power of the air handling system can vary greatly depending on the intended use of the wind tunnel. whether it's for testing miniature drone prototypes or full-scale aircraft. The meticulous engineering behind the air handling system of the wind tunnel is fundamental to its functionality. The control of air density, temperature, and humidity within the tunnel is crucial because these factors directly affect the behavior of the air and, consequently, the accuracy of the tests conducted. To put this into perspective, changes in air density, which can occur due to variations in temperature and pressure, can significantly impact the aerodynamic forces experienced by an object in flight. Engineers must, therefore, work diligently to maintain consistent and controlled conditions throughout the wind tunnel. Achieving this level of control is no small task. Engineers must draw upon their understanding of fluid dynamics, thermodynamics, and heat transfer principles to design systems that can precisely manipulate these environmental variables. For example, temperature control may involve elaborate heating or cooling mechanisms to maintain a stable test environment. Controlling humidity can be equally challenging, as it requires the careful regulation of moisture content in the air, which can affect air density and the flow of air over the test object. The precision engineering involved in wind tunnel air handling systems extends to the mechanical design of fans and compressors. The size and power of these components can vary significantly based on the wind tunnel's intended use. Wind tunnels designed for testing miniature drone prototypes may require relatively small, low-power fans, while those intended for full-scale aircraft testing demand massive, high-capacity air handling systems capable of producing extremely high wind speeds. In large, high-speed wind tunnels, engineers often incorporate multiple stages of fans and compressors to achieve the desired air speeds. These components must be meticulously engineered to withstand the extreme stresses generated by the high-speed airflow. The materials used in their construction must be carefully selected for their strength and durability, and the mechanical design must ensure that components can operate reliably and safely under these conditions. Additionally, the control systems governing the air handling system are highly complex. Engineers develop sophisticated algorithms and control mechanisms to regulate variables like fan speed, compressor pressure, and air temperature. These control systems must respond rapidly to maintain the desired test conditions, compensating for fluctuations in the surrounding environment and ensuring that the test environment remains stable and consistent. In essence, the engineering of the air handling system in a wind tunnel is a meticulous and multifaceted endeavor that embodies the intersection of various engineering disciplines. It requires a deep understanding of fluid dynamics, thermodynamics, materials science, and control systems. The successful operation of a wind tunnel hinges on the precision and attention to detail that engineers bring to each aspect of the air handling system, ensuring that the results obtained within the tunnel are both accurate and reliable, regardless of the scale or complexity of the tests being conducted. The heart of a wind tunnel is the test section, where the physical models or prototypes are placed to experience the simulated airflow. Designing the test section involves complex aerodynamic considerations to minimize interference and achieve accurate data collection. Engineers often use cutting-edge computational fluid dynamics, CFD, simulations to optimize the shape and size of the test section, ensuring it replicates real-world conditions as closely as possible. The test section of the wind tunnel is, indeed, the core component where the magic happens. It's the place where engineers place the physical models or prototypes they want to study in a controlled aerodynamic environment. The critical aspect of the test section lies in its ability to recreate conditions that closely resemble those experienced by the object in its intended real-world environment. To achieve this level of accuracy, engineers engage in a meticulous process of design and optimization. First and foremost, the shape and size of the test section must be carefully considered. These factors significantly influence the quality of data collected during experiments. If the test section is too small or poorly designed, it can introduce unwanted turbulence or boundary layer effects, skewing the results. Computational fluid dynamics, CFD. Simulations play a pivotal role in this phase of design. CFD simulations involve the use of advanced mathematical models and numerical methods to simulate the behavior of fluids, in this case, air, and the interaction of objects within them. Engineers use these simulations to predict how air will flow around and interact with the model in the wind tunnel test section, by tweaking variables like the shape and dimensions of the test section. They can optimize it to closely replicate real-world conditions. A critical consideration in designing the test section is the minimization of interference effects. Interference refers to any distortion or disruption in the airflow caused by the presence of the test model, supports, or other elements within the test section. Engineers aim to minimize interference to ensure that the data collected accurately represents the aerodynamic behavior of the model itself, rather than being influenced by the test section's structure. In some advanced wind tunnels, engineers go to great lengths to reduce interference. They may employ techniques such as boundary layer control, which involves using sophisticated suction or blowing systems to manipulate the airflow near the model's surface. This helps maintain a smoother, more uniform airflow and minimizes the impact of the boundary layer, which is the thin layer of slow-moving air near the surface of the model. Moreover, engineers also consider the type of airflow they want to create within the test section. Depending on the specific objectives of the experiments, the airflow may need to be steady and uniform, turbulent, or even include variations in temperature and pressure. The design of the test section and the air handling system must cater to these requirements. In essence, the test section of a wind tunnel is a critical area where engineering precision and attention to detail are paramount. Using CFD simulations and optimization techniques, engineers strive to create an environment that faithfully replicates real-world conditions while minimizing interference and other factors that could compromise the accuracy of the data collected. It's in this carefully designed and controlled space that breakthroughs in aerodynamics, aeronautics, and various other fields are made possible. Wind tunnels come in various shapes and sizes, from small, low-speed tunnels used for research and development to large supersonic and hypersonic facilities. Each type poses unique engineering challenges. Supersonic wind tunnels, for instance, must deal with the effects of shock waves, extreme temperatures, and high pressures. Engineers must employ advanced materials and cooling techniques to withstand these conditions. Supersonic wind tunnels are a prime example of how engineering ingenuity must contend with extreme conditions. These facilities are designed to replicate the high-speed flight conditions experienced by aircraft and spacecraft, where the velocity of airflow exceeds the speed of sound. In this regime, engineers face a multitude of unique challenges. One of the most significant challenges in supersonic wind tunnel engineering is the management of shock waves. As objects travel through the air at supersonic speeds, shock waves form, causing abrupt changes in air pressure, temperature, and density. These shock waves can interfere with the accuracy of experiments and measurements. Engineers must carefully design the test section, nozzles, and diffusers to control and minimize the impact of these shock waves. Computational fluid dynamics, CFD, simulations are often employed to optimize these components for efficient supersonic airflow. Furthermore, the extreme temperatures generated during supersonic testing demand sophisticated solutions. As air molecules are compressed at high speeds, they release heat energy, resulting in elevated temperatures within the wind tunnel. Engineers must select materials that can withstand these extreme conditions without deformation or degradation. Advanced alloys and composite materials with exceptional heat resistance are commonly used. Additionally, cooling systems may be integrated into the wind tunnel infrastructure to ensure that the test section remains at the desired temperature, preventing any adverse effects on the models being tested. Another crucial aspect of supersonic wind tunnel engineering is managing high pressures. The high-speed airflow generates significant pressure differentials within the tunnel. Engineers must carefully evaluate the structural integrity of materials used in construction to ensure they can withstand these forces. Lightweight yet high-strength materials are often selected to ensure the wind tunnel's longevity and safety. Aeroelastic effects also come into play when testing at supersonic speeds. As objects move through the airflow, they can experience dynamic deformations due to the forces exerted on them. Engineers must account for these aeroelastic effects when designing both the model being tested and the wind tunnel itself. Failure to do so could lead to inaccurate results and potentially compromise the structural integrity of the model. Moreover, achieving and maintaining supersonic airflow within the tunnel demands precision engineering. The design of specialized compressors, nozzles, and diffusers is paramount. Engineers must ensure a consistent and uniform supersonic flow for accurate testing. The field of gas dynamics plays a crucial role in understanding and optimizing these systems. Supersonic wind tunnels can generate intense noise and vibrations due to the high-speed airflows and shock waves. These can pose challenges both to the accuracy of experiments and the safety and comfort of personnel. Engineers employ noise reduction techniques and vibration damping systems to mitigate these effects. This not only protects sensitive equipment but also creates a safer and more conducive working environment for those involved in testing. Lastly, safety measures in supersonic wind tunnel engineering are of utmost importance. Due to the high velocities and extreme conditions involved, stringent safety protocols are implemented. Emergency shutdown systems, protective barriers, and ongoing maintenance are essential to safeguard equipment and personnel. The engineering of supersonic wind tunnels exemplifies the remarkable feats of engineering required to advance our understanding of aerodynamics and propel aerospace technology forward. The meticulous consideration of shock waves, extreme temperatures, high pressures, aeroelastic effects, and safety measures showcases the depth of expertise and innovation required to explore the frontiers of supersonic flight. These facilities play a pivotal role in shaping the future of aviation, space exploration, and defense systems by providing invaluable insights into the complexities of high-speed airflow. Wind tunnel instrumentation is another critical aspect of the engineering behind these facilities. To gather data during tests, engineers install a variety of sensors, pressure taps, and cameras inside the test section. These instruments are carefully calibrated to provide accurate measurements of forces, pressures, and aerodynamic parameters. The data collected helps engineers refine designs, improve performance, and ensure safety. Wind tunnel instrumentation is a pivotal component of the engineering marvel that is a wind tunnel facility. It involves a sophisticated array of sensors, pressure taps, cameras, and other specialized instruments meticulously placed inside the test section. These instruments serve as the eyes and ears of the engineers, enabling them to gather precise and comprehensive data during experiments. The sensors installed in the test section are designed to measure a wide range of parameters crucial for understanding how an object interacts with the airflow. These parameters may include airspeed, static and dynamic pressures, temperature, humidity, and angles of attack. Each sensor is carefully chosen for its specific role, and its accuracy is paramount. Engineers must consider factors such as the sensor's sensitivity, frequency response, and calibration to ensure that the measurements are as accurate as possible. Pressure taps, often distributed strategically across the surface of the model being tested, allow engineers to capture the pressure distribution around the object. This data is invaluable for understanding how aerodynamic forces are distributed and can be crucial in optimizing designs. Pressure taps are typically connected to pressure transducers that convert the physical pressure into electrical signals that can be recorded and analyzed. Cameras are another vital component of wind tunnel instrumentation. High-speed cameras capture the motion of airflow around the object in real time. Engineers use this visual data to study phenomena like boundary layer separation, shockwave formation, and vortex shedding. Advanced image processing techniques can further enhance the analysis, providing insights into complex flow patterns that might not be apparent through other means. Calibration is a fundamental step in ensuring the reliability of the collected data. Engineers meticulously calibrate each instrument to a known reference standard, often using specialized equipment and procedures. Calibration involves verifying the accuracy of measurements and correcting any discrepancies. This process is critical because even minor inaccuracies in data can lead to significant errors in the analysis, potentially impacting the design and safety of the object being tested. The data collected from these instruments serves several crucial purposes. Firstly, it aids in the refinement of designs. Engineers can precisely measure the aerodynamic forces acting on an object and identify areas where improvements are needed. For example, in aircraft design, engineers can optimize wing shapes and control surface configurations based on the data collected in the wind tunnel. Secondly, wind tunnel data is instrumental in improving the overall performance of objects subjected to aerodynamic forces. Whether it's enhancing the efficiency of an automobile's design to reduce drag or fine-tuning the wing profile of an aircraft for improved lift and stability, wind tunnel data guides engineers in making evidence-based decisions. Lastly, wind tunnel data is integral to ensuring safety. It helps engineers identify potential issues and instabilities in designs, which is particularly critical in aviation and aerospace applications. By thoroughly understanding how an object behaves in different aerodynamic conditions, engineers can develop safety measures and contingency plans to address unforeseen challenges that might arise during real-world operations. In essence, wind tunnel instrumentation represents the meticulous attention to detail and precision that underpins the engineering of wind tunnels. It is the conduit through which engineers gain valuable insights into aerodynamics, leading to advancements in technology, improved performance, and enhanced safety across various industries. In recent years, the field of computational modeling has made remarkable strides, offering engineers a powerful tool for simulating airflow digitally using supercomputers. This development has revolutionized the way we approach aerodynamic analysis and design. Computational fluid dynamics, CFD, is at the forefront of this digital revolution, enabling engineers to create virtual wind tunnel environments within the virtual realm of a computer. CFD works by dividing the fluid domain into a grid of discrete cells, each representing a portion of the airflow. Complex mathematical equations that describe the behavior of fluids, such as the Navier-Stokes equations, are then applied to each cell. These equations are iteratively solved using numerical methods to simulate how air flows over an object or through a specific environment. With the computational power of supercomputers, CFD models can analyze intricate details of airflow, pressure distributions, and turbulence in ways that would be challenging or impossible to achieve in physical wind tunnel experiments. However, despite the many advantages of CFD, it is not a standalone solution. Wind tunnel testing remains an essential component of the aerodynamic engineering process. The synergy between computational methods and experimental testing is driven by the recognition that both have their unique strengths and limitations. One primary advantage of computational modeling is its ability to rapidly iterate through various design scenarios. Engineers can tweak parameters and geometry in the digital realm, allowing for quick and cost-effective design exploration. This agility is particularly valuable in the early stages of development when multiple design concepts are being considered. On the other hand, physical wind tunnel testing provides the essential grounding in reality. It serves as a crucial means of validating the accuracy of CFD simulations. Real-world factors, such as manufacturing tolerances, surface roughness, and unaccounted for physical phenomena, can all impact the performance of an object in ways that computational models might not fully capture. Wind tunnel experiments allow engineers to confirm that the predictions made in the virtual world align with actual empirical data. Moreover, wind tunnel testing is invaluable for fine-tuning the final design. Engineers can identify specific areas where the computational model may have deviations from real-world performance. Subtle adjustments can be made to the physical model, and the process repeated until the desired outcomes are achieved. This iterative feedback loop is instrumental in refining designs to meet the stringent performance and safety requirements of aircraft, rockets, automobiles, and other aerodynamic applications. The marriage of computational modeling and wind tunnel testing is a pinnacle of engineering innovation in the realm of aerodynamics. It represents a harmonious blend of cutting-edge digital technology and traditional empirical testing, offering engineers unprecedented insights and capabilities. This synergy ensures that the complex challenges of aerodynamics are tackled with both precision and real-world validation, ultimately advancing our understanding of fluid dynamics and contributing to safer, more efficient, and more innovative designs in the world of engineering. Wind tunnels are not just engineering marvels, they are also symbols of human ingenuity and our constant quest for knowledge and innovation. These facilities represent the culmination of years of research, development, and refinement, driven by the innate human curiosity to understand and manipulate the forces of aerodynamics. The impact of wind tunnel engineering is most evident in the realm of aviation and aerospace. Since the earliest days of powered flight, wind tunnels have been instrumental in designing and optimizing aircraft. Engineers and aerodynamicists use wind tunnels to test and refine airfoil shapes, wing designs, and fuselage configurations. The data collected within these tunnels have led to the development of faster, more efficient, and safer aircraft, from the Wright brothers' pioneering flights to modern supersonic jets and spacecraft. Moreover, wind tunnel experiments have been crucial in advancing our understanding of fluid dynamics and aerodynamic principles. They allow scientists and engineers to study airflow around objects and how it affects lift, drag, and stability. This knowledge extends beyond aviation and is vital in designing everything from high-speed trains and race cars to wind turbines and even the aerodynamics of buildings. Wind tunnel testing aids in optimizing the performance, efficiency, and safety of these diverse structures and systems. In the automotive industry, wind tunnel testing is a cornerstone of vehicle design. Engineers use wind tunnels to assess the aerodynamic properties of cars, trucks, and even Formula One racing cars. By fine-tuning the shape and features of vehicles, manufacturers can improve fuel efficiency, reduce emissions, enhance stability, and increase overall performance. This is a direct impact on our daily lives, as more aerodynamic vehicles contribute to reduced fuel consumption and environmental sustainability. Architectural engineering is another field greatly influenced by wind tunnel technology. Skyscrapers and other tall structures are subject to complex wind forces that can affect their structural integrity and comfort for occupants. Wind tunnel tests help architects and engineers design buildings that can withstand various wind conditions while providing safe and pleasant environments for inhabitants. This engineering ensures that our cities can continue to grow taller and more innovative in their designs. Beyond these practical applications, wind tunnels also play a vital role in pushing the boundaries of scientific knowledge. They have been instrumental in exploring supersonic and hypersonic flight, as well as studying the aerodynamics of spacecraft during re-entry into Earth's atmosphere. These endeavors are critical for space exploration and have led to advancements in satellite technology and space shuttle design. In essence, wind tunnels stand as testaments to the human spirit of inquiry and innovation. They embody our relentless pursuit of knowledge and our commitment to pushing the boundaries of what is possible. These facilities have transformed industries, shaped our understanding of the physical world, and continue to be essential tools for engineers and scientists as we navigate the complex challenges of aerodynamics with precision and confidence. They are, without a doubt, a shining example of the power of engineering to change the course of history and the future.